We're very pleased to have Fiona Porter from University of Manchester. And if I'm correct, you're going to talk about uncertainties in CNN classification of one type of galaxies, which are radio galaxies.
That's it.
Which can obviously be applied to other kind of classification. So I'll leave you the screen. Thank you very much.
Thank you very much for inviting me. So as Philippe said, my name is Fiona Porter, and I'm currently a final year PhD student at Jodrell Bank Centre for Astrophysics at the University of Manchester. So today, I'm going to be talking to you about why we need machine learning for radio astronomy in general, some of the limitations that come with machine learning, and then we're going to talk a bit about how you can quantify the uncertainty in machine learning models and some of the things that you can use these uncertainties for. So to get us started, first question is, why do we need machine learning anyway? So as some of you may be aware, there are several radio telescopes that will be constructed in the not too distant future, fingers crossed, which are going to really dramatically increase our understanding of the radio sky. So the big one of these is, of course, the Square Kilometre Array. And this will have a depth of field that's absolutely unprecedented for a radio telescope, really high sensitivity, really high resolution. So we're going to be able to detect all sorts of sources which we previously just couldn't, with the caveat that we're going to have to find the sources in amongst all of that data, which is not a trivial thing to do when the data rate is expected to be of the order of about a terabyte per second. Now, traditionally, source labeling would be done by astronomers just looking through the data, finding sources of interest and labeling them with the appropriate class. But that's clearly not practical with this much data. Even if astronomers did nothing else with all of their time but label data, we still wouldn't be able to keep up. So we need new techniques. Now, correctly identifying these different sorts of astronomical sources often requires a degree of expert knowledge. It can be quite difficult to tell different classes apart from one another. But the first thought might still be, can the public help in some way? And the answer is yes, to an extent. So there are some citizen science projects where volunteers from the general public are shown survey data, and we ask them to label it with what they see. If you're not familiar with Galaxy Zoo, that's one of the lead projects of the greater Zooniverse, as it's called. And over here on the right is an example of the interface for the Galaxy Zoo project. So this is for galaxy classification. And volunteers start out by being asked, is the galaxy smooth? Does it have any features? Or might it just be a star? And once they've selected one of those, they can go into further questions. So we can get some quite detailed information about morphology. But with this said, our citizen scientists are the general public. And because of that, they don't have the sort of knowledge that means that we can take any one person's word for it that their label is correct. And not even if they are completely innocently just trying to do their best, they can make mistakes sometimes. It just happens. So instead, what we need is a consensus from multiple people all classifying the same source. The more people, the better. And what we hope to see is that a lot of people will label the same source the same way, in which case we can say, great, they're probably right. We can move on with that one. But if there's a lot of disagreement, that's something which we, again, need experts to have a look at and make sure what's going on. So because of these two things, this method is even slower than the traditional one of having astronomers label things. So this won't work either. So naturally then, we want to turn to machine learning, which is capable of classifying thousands of images per second, which obviously no human can manage, with classification accuracy near the levels of human experts, depending a bit on exactly what the classification problem is and how complex the model is. Now for this talk, I am going to focus on convolutional neural networks, which are a very popular choice for image classification, both in astronomy and in other fields. So they are modeled after the human visual cortex, and their base unit is the artificial neuron, which, just like the neuron in the human brain, receives a signal, and then depending on some properties, it may pass that signal on, be activated, or it may not. So multiple convolutional layers can detect increasingly complex features. At their most basic, this might be something like detecting an edge or detecting a corner, while progressively deep ones can detect things which are really quite complex. So if you've ever come across a passport gate, which lets you scan your passport and look at a camera to confirm it's you, that's the sort of face recognition that these sort of high-level convolutional layers are looking for. And we provide this model with labeled data. We tell it what an image is, and from this it learns which features it detects are associated with each class. And again, putting this in human terms, you can think about how for small children, for a while, every four-legged animal is a dog. And they'll see an animal and just say, oh, that's a doggy. And their parents will go, oh, no, actually, that's a cat. That's a fox, something like that. So the toddler then learns the features which are associated with each animal. Fortunately, humans can do, machine learning models rather, can do this a lot faster than human children are. So instead of a training time of however many years, depending on model complexity, this can be anything between, at the fastest, under an hour, and then for more complex models, maybe weeks or months, but still a lot faster than teaching children. Now, once it's been trained, a CNN can then predict the labels, the classifications, for images which it hasn't seen examples of before. So if we have trained it on cats, then if we show it pictures of a cat which is not in its training set, it can then correctly label other cats. And it will output its predictions as a softmax probability vector. So this is a normalized probability of the image belonging to each of the classes the model has been trained on. But there are some limitations to this. So to start with, softmax probabilities will often be like examples of the image here on the top left. This was a very basic cat-dog classifier that I trained for this. And my model thinks this is 99.5% likely to be a dog, 0.42% likely to be a cat. That's usually how these different probability vectors look. It's just a list of different probabilities that sum to 1. The problem is we often treat very high probability as meaning the prediction is very reliable. So this is a problem for two main reasons. The first one is softmax probabilities don't have associated errors. You'll notice that when I gave those numbers, there's no plus or minus there. There's no uncertainty being expressed, which is something which we in astronomy are, usually very keen on. We like to know what our uncertainties are. We don't know what these uncertainties are, and because of that, we have no idea if the confidence that this model is expressing is warranted. Obviously, in this particular case, as humans, we can say, yes, that is a dog, but the model doesn't distinguish. And a good example of this having an effect is in that it's possible for an image to be classified with very high probability and be completely wrong. Is this image on the bottom left, which is my favorite example of this sort of issue. So this, without the piece of paper, this particular model classifies correctly that this is a Granny Smith apple. If you just stick a piece of paper on it that says iPod, 99.7% probability, according to the model, that it is an iPod. So this is a weakness of this particular architecture, but it does demonstrate that you just can't rely on softmax probability alone. And as well as these, there's one more issue which is of particular importance to astronomy, which is what if the correct label isn't any of the labels that the classifier has been trained on. These are called out-of-distribution sources, and it's pretty important to be able to pick them out of the rest of the data. At the sort of less interesting side of things, these could be artifacts. It could be noise in the image, maybe a Starlink satellite flew through it. There's something in the image which has spoiled the data and it's not really anything. And if this gets left in, then this can then damage our data sets going forward because we've got stuff in there which shouldn't be in there. On the more exciting end of things, these could at times be types of astrophysical objects which don't really look like anything we've seen before. And theoretically, it could be an entirely new field being opened up there. So potentially very exciting. But again, we don't want it to get lost in amongst the other data. We need to be able to separate these types of sources, and we cannot do that with softmax probability alone. Now, to demonstrate some of these problems I will get to the astronomy, I promise, but to start with, I'm using the cat-dog classifier again, because that's a lot easier, I find, for people to understand the features of than going straight to the astronomical sources. So on the whole, this model has about 90% classification accuracy. It's not incredibly accurate in terms of these things. We could do better, but this is just a quick little demo, so it doesn't especially need to be. So both of these images here are being labeled by the model as having more than 99% probability of being dogs. And of course, you can see the obvious problem with that, because one of them, to human eyes, very definitely isn't. But despite that, the CNN is not only saying that it's a dog, it's saying it's more likely to be a dog than the dog is. So that's a clear reason that you can't just say, we will ignore all sources which have less than 90% predicted probability and just get rid of everything below that, because you can be very confident and very wrong. So let's have a look at out-of-distribution objects. So I tried this out on two types of animals, foxes and ducks. And the reason I tried foxes out was because I suspected that what the model would do is pick up some cat-like features and some dog-like features. So for example, foxes obviously have those triangular ears, which are more distinctive to cats, but they also have a nose shape a lot more like a dog. And true enough, what seems to happen is if you take a picture of a fox from the front, the model thinks it's more likely to be a cat. And if you take it from the side, so it shows the nose, it thinks it's more likely to be a dog. And this could be a sign that the long snout is one of the features the model thinks is very likely to make something a dog without having any other evidence. Because the model was also very confident that the images of ducks that I showed it were also dogs. So that is 99.98% probability, according to this model, a dog. And my guess is that lacking any other features to pull from, it can't find any ears, it can't see a tail, it's decided, well, we'll just go with the nose. That'll do, that's our best guess. And it doesn't have any cat-like features, so it's very definitely a dog. And as I mentioned before, all of these images have very normal softmax probabilities. They're all values that we might expect real cats and dogs to have. So how can we tell that they shouldn't be there? And this is where uncertainty comes in. We need a method of expressing uncertainty in the predictions that our models make. And ideally, they should do at least one of two things. We want them to be able to tell us how likely the model's predictions are to be reliable, which doesn't necessarily mean the model has a very high softmax probability. In some cases, it's much more valuable to know that a model thinks that a source is 80% probability to be a certain class, but it's absolutely, absolutely sure it's 80%, as opposed to something it thinks is 99% likely to be a class, but it's a bit uncertain about exactly how high or low those values could go. And the other thing we want it to do is tell us why the predictions might not be reliable. Is it because of an issue in the model, or is there something in the image that doesn't belong? So the rest of this talk is going to discuss how we calculate and use some of these different uncertainty measures. Uncertainty in a machine learning model comes in two varieties, which are called aleatoric and epistemic uncertainty, which I always get mixed up, so I will do my best not to confuse them throughout the talk. So aleatoric uncertainty is uncertainty within the image due to the properties of whatever is pictured in the image. So there are sometimes images have features within them which are just difficult to conclusively identify for humans or for machines. And because this is an inherent property of the source, you can sometimes reduce it by using a higher resolution image, or if there are confusing background sources, you can remove those. But you can't get rid of it entirely unless you actually change whatever it is that's being pictured, which is usually quite difficult to do for astrophysical sources. Epistemic uncertainty, on the other hand, comes from limitations in the model's ability to predict confidently. All models have a finite amount of training data they can learn from. There's a limit to how much data there is in existence. So their understanding is limited to what they've seen before, effectively, and they can extrapolate a bit. But to use another example here, if you have only ever shown your model pictures of black dogs and orange cats, it's going to be very confused if you then start showing it an animal, even another cat or dog, which comes in a different color, because it might well have used color as one of the main features of how it makes its predictions. Now, this type of uncertainty can be reduced, theoretically not down to zero unless you've got an infinite data set, but you can reduce it by ensuring your training data set is as large and as representative as the population of whatever you're classifying as is practical. And because these are a little bit obtuse, here are some image examples of this. So the image on the left is an example of high aleatoric uncertainty. It is in distribution. It is a cat or a dog, guess which. But it's going to be difficult for the model to classify because the features it can use to classify aren't very clear. Now, in the case of this particular animal, you can fix this quite easily by just taking a new photo from a different angle. But of course, you can't do that with astronomical sources like the ones we're interested in. They're too far away. We can't interact with them. Even us moving through space isn't going to change the perspective we see of them very much. So in our case, we can't do anything about aleatoric uncertainty. Now, the image on the right has high epistemic uncertainty. It's out of distribution. The model just doesn't have the data it needs to be able to classify this. And in order to fix that, what we need to do is give the model training data, which includes this image class. You can get a similar effect if you have trained your model on just too few images in general. So this is why we sometimes use things like augmentations to increase the number of images we've got to work with. Now, during the training process, a CNN's weights are optimized to find the best possible model to predict the classes that it's trained on for the problem it's working on. And once the training is complete, the parameters are then fixed into place. So the model will always give exactly the same predictions for exactly the same image, which is usually what you want. You want a model which gives very consistent predictions. Otherwise, you could end up with completely different results just at random. But it does raise the question, if the response is always the same, doesn't that mean there's not really any uncertainty we can get out of it? There are a couple of different methods which the machine learning community has looked into to express uncertainty during training, but they tend to involve adding additional parameters which make models more computationally expensive to run and to train. Instead, we're going to actually look at a slightly unusual application of dropout, which reduces computational expense, which is always good. So again, if you aren't familiar, dropout is a regularization tool commonly used in CNNs, which prevents overfitting, which is when the model performs well on its training data, but this performance doesn't reflect how well it does on other data. It's become overly optimized towards the training data. And what it does is randomly drops out a fraction of the model's neurons, and they then can't contribute to the model's classification. So if you do this, it stops the model relying too much on any individual neuron for its predictions, because sometimes it's just not available. Dropout is usually turned off once a model is trained, because otherwise, again, the outputs would vary, but we want that. So what we can do is add a dropout layer right before the layer which gives us our classifications, which we turn back on for our trained network. So every time the model is initialized, different neurons are dropped out, and the model's predictions will vary between iterations. How much they vary is going to be our metric for uncertainty. Ideally, for a prediction they're very confident in, we're expecting this variation to not be very much, whereas something that's a lot more uncertain of course, it's going to vary much more. So here are the actual mathematical representations of some of our metrics. This first one is entropy, and it's a measure of overall predictive uncertainty, epistemic plus aleatoric. And it expresses how highly a model predicts one class over all other possibilities. So what we are doing is we are running the same image through a network t times. And each time we do it, we calculate the probability that the model has assigned to this class belonging to this image belonging to a particular class. As you can see here. So this is minimized when the predicted probability for one class is consistently 1. So as you can, this is fairly trivial to see. 1 log 1 is 0, and 0 log 0 is 0. So minimal entropy is 0, which means the model is always predicting something with 100% probability. This still doesn't necessarily mean it's right, but it does mean the predicted probabilities are consistently high. Now, one thing that entropy doesn't do is distinguish between the probability being consistently high for one class or alternating consistently high between both. So for this, we turn to mutual information. This is a measure of model uncertainty, of epistemic uncertainty, and expresses how confident the model is in its own predictions. And it's calculated as the difference between entropy and entropy's expectation value. Again, this is a little bit obtuse at times, so here's some examples. If we've got an image which we have run through our classifier however many times, and 50% of the time it's saying this is 100% class 1, and the other 50% of the time it's saying it's 100% class 2. This can have a very low entropy because the model is consistently doing some very high predicted probabilities, but it will have high mutual information. So our model right now is overconfident and inconsistent. It doesn't realize that it can't predict with confidence. On the other hand, if we've got an image which every single time it's predicted to have 50% probability of being class 1, 50% probability of being class 2, the entropy will be high, but the mutual information very low. The model is uncertain, but it knows it's uncertain. It's very consistent. And so because of that, we can actually probably trust what it's saying about this particular image more, despite the fact that the predicted probabilities are very low. And then finally, so while you're using softmax probabilities, you are using normalized probabilities. They have to sum to 1. The probability, as far as the model's concerned, that the image you're showing it is one of the classes it knows of is 100%. But this is not exactly how it's calculated within the model. That's presented in a way for humans to understand it. What you get before softmax are non-normalized probabilities called logits probabilities. And you can actually plot these as distributions in latent space, in feature space. And what you might reasonably expect is for different classes to form different clusters in feature space. And indeed they do. And you can fit them using a Gaussian mixture model, which is a type of unsupervised learning algorithm, which essentially you inform it, I would like you to fit these data points into this many clusters, and it finds the best possible solution for you. So using these Gaussian mixture models, we can then calculate a score for any image, which gives us the probability of it belonging to any particular cluster. This is another measure of epistemic uncertainty. Densely populated regions of the latent space are ones where the model has a lot of information about it. It's seen a lot of sources which represent that particular area. So it has low epistemic uncertainty, good model understanding. And in the meanwhile, areas which are sparsely populated are ones which it doesn't have much information about and therefore has high epistemic uncertainty. So now let's get on to some actual astronomy. I'm going to be doing this work with some Fanaroff-Rayleigh galaxies, which are radio-loud active galactic nuclei. So the difference between these two classes is morphological. They both are centered upon the host AGN, and the difference between them is where the jets they emit are brightest. In the case of FR1s, they are brightest closest to the core and get dimmer and diffuse further out. In the case of FR2s, they're usually somewhat bright near the core, but most of the emission is concentrated in big radio lobes. And you can see the two examples here. It's believed that the same underlying mechanism produces both, and it's principally a difference in the nearby intergalactic medium which causes the different morphology. The dataset I'm using for this is one which I put together. It's called Minerva-Live and comprised of 1,256 FR galaxies. And as well as being labeled as either FR1 or FR2, they're also labeled as being either confidently classified or uncertainly classified by humans. So the confident ones, the ones we are absolutely certain are the FR class they're labeled as. The uncertain ones, we believe they are, but we're not completely sure. And this is a publicly accessible data set. So if you are interested in having a go with it, it can be found on Zenodo. The architecture that I'm using is a modified version of Linnet, so very popular benchmarking architecture with some additional parameters. I'm using some spectral normalization to regularize the parameter space, which is effectively just trying to prevent out of distribution sources from being mapped to in distribution areas. And as I mentioned previously, I've added a dropout layer before the classification layer to give us that variation in outputs. And I've created two models for this. One which was trained exclusively on the confidently classified images. I'll call that the confident model going forwards. And one which was trained on all the FR galaxies, regardless of confidence. And that's the full model. So what we see on the whole is that the models have fairly similar accuracy. The full model is slightly better, 87.1% accuracy versus 85.7%. And broadly speaking, we've got similar trends in terms of entropy, which is what's plotted here. One thing you do see, though, is that the full model has noticeably more images with very high entropy. And given that entropy is a way to express how much the model's predictions vary over different iterations, that might make you wonder, is the confident one then a better classifier? And it turns out the answer is actually no when we look at the breakdown of these sources. So here our top row are colored according to whether they were correctly or incorrectly labeled, as well as the confident versus uncertain dichotomy. And the bottom row are labeled with their mutual information. So what we can see in the top row is that for the full model, incorrectly labeled sources tend to have high entropy. So this suggests that the model is aware that it doesn't really know what's going on for these particular sources. On the whole, it's doing all right. On the other hand, for the confident model, incorrectly labeled sources have quite a wide range of entropy values, suggesting the model isn't really aware of what it doesn't know. And a similar thing is reflected in the mutual information scores. The highest mutual information sources are all in the highest entropy bin. So these are the sources that the model is expressing maximal uncertainty about, and they're all ones with very high entropy. So great. On the other hand, the confident model has a much wider spread of mutual information values. You start seeing very high mutual information at lower entropy scores. So again, this is suggesting that our model is overconfident, especially when it comes to uncertain sources. So what this suggests on the whole is that by using a curated data set with images which humans are confident about the labeling of, it makes the model become overconfident in its own ability to make predictions on images which aren't as nice as the ones which it's seen before. So I did mention earlier that softmax probability isn't a good representation of predictions correctness. So you might wonder, are there any potential issues in using it to calculate these evaluation metrics? And according to Mucotti et al., who I cited earlier in this, yes. For sources with high epistemic uncertainty, entropy can take arbitrary values, which obviously also affects mutual information because it uses entropy in its calculation. So this is the part where we turn to some Gmm scoring. So this is the result of plotting our data in feature space. The yellow cluster here is comprised of FR2s, and the purple cluster is comprised of FR1s. The color mapping extends to sources in other areas. If it's yellow, it's being predicted as an FR1. Sorry, its true class is FR. Sorry, if it's yellow, its true class is FR2. If it's purple, its true class is FR1. So you can see we do have some misclassifications throughout. But what you're seeing in terms of overall behavior is that there's a bit of a scale in terms of the predicted probabilities for these. Towards the center, you're getting somewhat ambiguous sources. The model isn't completely sure what they are, and they're also a bit more likely to be ambiguous to humans as well. Towards the centers, you're getting some much more obvious classic FR1 and FR2 morphology, and this extends right out to the far ends where the model is really absurdly confident. Now, one thing I would like to highlight is this inset image here, which the model predicted with very high softmax probability to be FR1. It's actually an FR2, but as you can see, there's clearly been some issue in the image processing for this particular image because it honestly looks very, very noisy. So we might be able to pick this up through other methods, but it's very obvious in this particular case, despite this being an image with a very high softmax probability, it's very far removed from either of the clusters. It's very clearly an outlier. So this is one that we should be able to pick up very quickly, should not be there, and its classification isn't reliable. And so, like I said, there's a clear region of overlap for this model. Not entirely surprising, though, given that both classes of FR galaxy are believed to come from the same underlying mechanism. There is ambiguity in reality. And the sources in this overlap region do tend to be the ones which are labeled as uncertain by humans. Proportionally, there is much more in the way of uncertain sources in this region than anywhere else in the plot. So the model and humans generally agree on which sources are ambiguous. So while they might not be picking up on the same features necessarily, they do agree. So that's good. As far as we can tell, models and humans are uncertain about similar things. So we should be able to understand why they're uncertain about things usually. Some of the sources the model is very confident about in terms of all of the metrics I've talked about so far are in quite sparsely populated regions of feature space. Flicking back a moment, like at the far ends of each of these ellipses, we're getting images which are very, very, very confidently predicted in terms of softmax. So can we use these results to select sources that could benefit from human validation? And the answer is again, yes. So what I've done here is calculated a GMM score for every data point in feature space. Excuse me. So this represents essentially just how close a data point is to the center of either of these elliptical distributions. Whichever one is the highest, that's the score that I use. So in this case, the color map here indicates the highest GMM score, but the size difference represents the difference between the two scores. So the score for the FR2 cluster minus the score for the FR1 cluster. So if they're large, it's got a high score for one component. So that would be, for example, near the center of the distribution. And if it's low, the scores for both are very similar. So this has an immediate effect that the clusters are now much more obviously separated. So whereas before it was quite difficult to tell exactly where the overlap occurred, now we can see it is right there. Most of the misclassified sources, which are the ones plotted here in red, are located preferentially between the cluster centers and the overlap regions. Unfortunately, there's not much we can do as of yet to remove the points near the cluster centers because they've got high GMM score. They often have high softmax probability, low entropy, and low mutual information. This might be in part because we are using a fairly simple model as proof of concept here, so we might need a deeper or more complex model to be able to pick these out properly. But we can still use this to flag sources for inspection. So these are the same sets of plots as before, and I'm highlighting sources as candidates for removal by calculating the modulus of the GMM score for the FR1 cluster and the GMM score for the FR2 cluster. So in these plots now, the color bar is as previously. Sources which have been removed and were correctly classified are orange, and sources which were removed and were incorrectly classified are red. So this is quite good for flagging regions where entropy and mutual information are likely to be unreliable. It's focusing around the edges of our distributions. But this does include a lot of correctly classified sources as well. If you have a look at the different misclassification rates, this is taking out usually something in the vicinity of 75% of the sources it removes are actually correctly classified. So this should be used with some caution. It can be good for spotting any obvious outliers, but you don't want to simply remove all of these from consideration because a lot of them are still good sources. As I've said before, most of the misclassifications are located in the overlap region. So I'll use a different method to flag just those. So what we're calculating here is the modulus of the difference of the GMM scores divided by the GMM scores being added together. And this preferentially flags things right in the center of the image, of the two distributions rather. And up to a value of 0.4 for this, this metric, the number of sources this removes which are incorrectly classified, the ones we want to remove, it works out as about 36 to 37%, which doesn't sound incredible, but if we were just randomly selecting sources to remove, we'd expect about 13% of them to be misclassified. So this is noticeably better than just taking a random cut. And you might wonder, well, why can't we just do this with Softmax? What happens if we try that? And it does start out with removing a very high percentage, relatively, of misclassified sources, but it's also very clearly biased towards the FR2 cluster as we increase the threshold to remove sources. Pretty much everything it's removing are FR2s. So this might be due to some biases in our model, but it's not something which impacts the GMM score. As we've seen previously, that was selecting things from both sides more or less equally, whereas this one is clearly leaving in a lot more sources it thinks are FR1s. So with that said, let's quickly have a look at some applications of uncertainty for different tasks. And I've already talked about uncertainty metrics being able to give information about how consistent a model's predictions are, finding whether or not sources are in distribution or out of distribution, and finding regions of feature space where we expect many images to be misclassified. And as well as this, images with high aleatoric uncertainty are valuable in datasets because real data isn't always tidy. Some sources are genuinely ambiguous, and as we saw earlier, if our models never see ambiguous sources, then they become overconfident in trying to classify them later. We can also make use of high aleatoric uncertainty images for a couple of other machine learning applications. So we'll start with GANs. These are generative adversarial networks. And the principle behind these is that you have two different models competing against each other. One of them is using real data as inspiration to create fake images. And the other one is trying to learn how to tell apart fake images from real ones. And as they compete against each other, they both improve. And the results from this can be really very convincing. You may have come across the websites such as "This human does not exist." Those are all randomly generated people constructed by GANs, and a lot of the time you really can't tell that they aren't real photos of people. These images over here on the right are ones which were generated by a former co-worker of mine, David Bastian. One of these is a real FR2 galaxy, and one of them is a fake. And he passed a sheet around the office for us to try telling which of his data sets were real and which were fake. And honestly, the lot of us who work with FR galaxies really struggled to get any better than random guessing. If GANs only see non-messy data during their training, so that's low aleatoric uncertainty, they won't be able to generate sources which show ambiguity. And that's actually a concern because quite often in astronomy, at least in my field of radio, we end up with source populations where we only really have a few examples of the sources that we'd like to classify. So we need to artificially supplement that. And one of the methods to do that is use GANs to create artificial sources which match the properties of real ones very well. So if we're going to do that, we want to have those more ambiguous sources in amongst our data. And the second application I'd like to highlight is for active learning, which is a way to get around the need for having large labeled data sets. GANs rely on having a small sample of labeled images and then a larger sample of unlabeled ones. While it's training, it can regularly ask a human to label one of the pieces of data it's not sure about, and it then uses this to decide which class things belong to. It uses it to refine its decision boundary. And it's much more useful to an active learning model to get information about a very ambiguous source than a very clear one, because these are the ones which will sit close to its decision boundary and can help it really refine how it makes its choices. So when we're using things like active learning, we want to make sure that we can provide them with images with high aleatoric uncertainty, so they can have the best possible way of learning how to distinguish between the different classes. So, in summary, uncertainty can give insight into the reliability of your model, and we expect this is going to be quite important, especially for big data surveys, where it's going to be really vital to be able to tell apart sources which belong but are just slightly ambiguous and things which are genuinely out of class. Over-curated datasets can harm a model's ability to identify its own uncertainty when it just doesn't have enough information to make accurate predictions. So because of that, you want your data to be slightly messy. Generally, images which humans find difficult to classify also have high aleatoric uncertainty. Humans and machine learning models are generally uncertain about the same things, although not necessarily for the same reasons. If we look at our data in latent space, we can identify regions where a model is being overly confident in its predictions or genuinely unable to classify well, and that lets us flag sources for human intervention. Finally, morphologically ambiguous sources have beneficial impacts overall for training other types of machine learning models. So being able to identify these is really quite useful for machine learning as a whole. So yes, thank you very much for inviting me to talk today.
Thanks a lot.
So yeah, if anyone has any questions, I'd be more than happy to take them now.
Yes, we have time for questions. So I have one small question.
Sure.
In the example you give, you have two classes that you separate. It's a very naive question, but if you would have a more diverse classes, how it would affect your clustering metrics? I mean, the one you define to identify the bad guys.
That's a good question. So theoretically, it is possible to calculate a Gaussian mixture model multidimensionally. There's nothing to stop it. I just happen to be using a two-class classifier, but theoretically you could expand this to more dimensions. I would imagine it should likewise be possible to establish a metric which lets you tell how different the different scores are from each other. Exactly how you'd calculate it, though, I think might need a little bit of extra thought, but we still would be looking at, I think, I imagine in that case, we'd probably in part want to look at things like which of the clusters give the most similar results and things like that. So the short answer is I haven't tried it yet, but theoretically it should work on the same principle.
Thanks. Remy?
Yes, thank you for the talk. It was very nice. I have a question about your last layers. You applied MC dropout to it.
Yes.
So I was wondering how much neurons you have on it, if you and how much dropout, and if you noticed a change of how it changed your uncertainty when you play with it.
Right. Okay. Well, I honestly, off the top of my head, I am not completely sure how many neurons I have in that final layer. It is just a standard Linnet architecture, so this is something which I should probably know off the top of my head, but unfortunately I don't. But the dropout drops approximately drops out 50% of the neurons involved. In terms of the uncertainty effect, if you turn the dropout off, you do get, on the whole, slightly better accuracy. And when I plotted, for example, this image in feature space, the softmax results that I'm plotting here do correspond to the results of the model with dropout turned off, just so I can get consistent results. Because obviously, if I kept dropout on, I'd get different positions every time I ran the model. But there is a variation. How much it varies in terms of feature space doesn't actually necessarily correspond very well with what you see in feature space here. So one thing that we observed is there's actually a much wider spread between very high predicted probabilities than there is for comparatively low ones. So there's a lot more of these images. I mean, you can see here that near the middle of the cluster, we're getting something like 99% probability, and then right up the far end, 100%. Meanwhile, towards the center, things change a lot faster. And I'm not sure if that answered what you were looking for.
Yeah, no, it's okay. Yeah, thank you.
David, well, I don't know which David starts.
I could perhaps. Thank you, Fiona. This was a really wonderful talk. If you can move to the next slide, perhaps. Oh no, yeah, this one. Yeah, with the GMM clusters. Mm-hmm. Yeah, I think the previous one, perhaps.
Oh, this one's still?
No, not perhaps next after that.
No, there we are.
Yeah, this one, perfect. Yeah. So, you know, I would expect the red points to be somewhere in between the two clusters, but many of them are close to the core of the FR2 cluster. So, what sort of sources are those, which are so misclassified so badly, right?
Honestly, the answer is disappointingly, they often aren't actually all that. Like, a lot of them do just look like, for example, fairly standard FR1s being mixed up for FR2s and vice versa. There's not really any obvious features about them, which, at least for them as a whole population, which explain why the model's getting them mixed up. And I think it is more down to just the limitations of this being a fairly simple model. And the main reason we used Linnet is the basis that any sort of uncertainty effects we are seeing are going to be much more down to the data set than some sort of complexity of the model architecture, or at least we think so. Sure. So a lot of the time, it's a bit harder to see, but you actually also get misclassified sources right out towards the sort of very confident areas too. I don't know if you can see my mouse on screen. I can't.
I can't, but there's some other.
Mm-hmm. Yeah, so there are some out there. There are some which the model just isn't very good at classifying for no really obvious reason.
Right. And my second question, if I may, do you have any examples of a radio galaxy with only one lobe? In which case, how would that work out?
This is actually something we have started looking into. We focused more on hybrid sources, which show FR1 morphology on one side and FR2 on the other. What you might want to look at in that case is, I believe, there's a subclass of FR1s, which I believe are called, wide-angle tail, which look a lot like they've only got one lobe. But the problem with trying to have a look at how it would respond to those is the population we know of them is really very small. There are some actually included in Minerva-Vest's data, but I think we've maybe got something like 5 of them. Right. It's already a very small population. And while it would be really interesting to see how it responds, like, is it going to base its prediction based on what it can see of that one lobe, or is it going to get confused and put it somewhere else entirely? And the short answer is, at the moment, we just don't have enough data points to really get, a statistically significant result. But it is very much something which we're looking into. So,
thank you.
Yeah, thank you, Fiona. It was a really interesting talk, really useful for a lot of us, I think. Yeah, I was having quite a tricky question, I think.
Okay.
Okay, so let's consider the case where you are trying to classify ships, and ships in the animal in a landfill.
Ah, right, yes.
So it was shown that when you are trying to do that, because most of the ships are in landfill, usually if you show a landfill, you will just classify it as a ship.
Yes, yes,
Okay,
I've seen
so
this problem. I've seen this problem. I thought it was really interesting.
yeah.
It is a slightly tricky one to deal with, I think. We do have something of an advantage in astronomy, though, in that I'll just move over here to some of my images of the different galaxies that I'm classifying.
Mhm.
They don't really have a background, most of them. The radio background is obviously fairly quiet, and unless there's a background source very obviously there, we can broadly expect that we're not really picking up any background information because there just isn't any. But it is 100% a bit of a concern that it might be possible that our classifiers are picking up on something which is really just a background feature. And yeah, I did see that particular, I believe that was by Janelle Shane.
Yeah, maybe.
Yeah, no, she's got a very good book about this sort of thing. And one of the other examples she gave was of things like if you pick up a sheep or a lamb or something, the model that she was using would quite often classify it as a cat or a dog because it just didn't understand that you can pick up a sheep. So there are some, I think for this, we're probably looking a bit more in the way of the sort of multi-object classifier, which can, put bounding boxes on different objects within the image. Theoretically, there should be a way to express uncertainty in these too. I know I've seen a paper recently concerning AI for self-driving cars, which had the problem that one of the images that they demonstrated this with was of a moose walking onto a road, and the model just didn't know how to handle that. I believe I'm not sure what it misclassified it as, but I think it might have thought it was a person. I'll see if I can find that paper and pass it on if you'd like. But they did have some success in getting their model to express uncertainty in labeling when it was able to bound boxes on things which it then couldn't find a good match for in its knowledge base. So it can be done. I'm afraid I'm not completely clear on how at the moment.
Yeah, because it's a case where the network will be very confident that it has found some features, but it's not the features you wanted to see. So I was wondering where it would end up, where you think it would end up in your GMM clustering or in your, I don't know, maybe directly with the entropy score. If you think it will be feasible to at least diagnose that you are in such a case?
See, what I would suspect is if it's pulling that strongly from, a background feature, I would expect it to be somewhere within the body of the distribution. I would not intuitively expect that it would be very clearly separated because, in the case of the sheep, it's clearly decided that a field is a characteristic of a sheep. So if that's the case, if it's using fields as one of its main features, then even a field with no sheep in it is probably going to be quite near the main cluster.
Yeah. Okay. Okay. Thank you very much for the precision, and I really want if you can send me this last paper about the moose, I will be really interested. Thank you.
Sure, no problem.
I have another super short question. It's about the sample you used.
Yes. Let's see.
How was done the classification?
So I pulled this from a paper by Miragai and Best, so that's why it's called Mira-Best, who had found a population of Phaneroff-Rayleigh galaxies within first, VLA first. And they classified everything by eye effectively. I believe they had the two authors looked through the images which were flagged as being potential FR1s based on previously catalogued information and just looked at them and said, this is an FR1, this is an FR2, and then added a label for how confident they were in that class.
So how many sources are we talking about?
A grand total of 1,256. There's really not very many. Like, that is, to my knowledge, the largest data set of FR galaxies in existence. We really don't know all that much about them in terms of, we haven't detected that many. So that's kind of why, in a way, we picked these for this particular issue, because they represent a very obvious problem in astronomy, where often we don't have very many sources that for the classes we'd like to classify. So if we can get it to work for FR galaxies, we ought to be able to get it to work for these other classes which only have a very small population of known sources.
Yeah, very interesting. Okay. Thank you very much.
Can I ask a question?
Yes, sure.
I would like to suggest that you use the Rogue Catalogue, which is a much larger catalog than the one of Miragai at best, and maybe Dorota Kozioł-Wierzbowska can say about it because she's listening to you.
Oh, okay. I wasn't aware of this one.
Yes, it came out 2 years ago, I think. It's called Rogue One, and by Dorota Kozioł-Wierzbowska et al. Dorota, if you are here, maybe you can say something. Maybe she's not listening. I can send you I will send you the reference in the chat.
I'd very much appreciate that. That'd be, yeah, having more sources would be great.
Hello, hi. Very nice talk. As Grażyna said, we've published the catalog of radio sources with a little larger number of sources and classification than Best and Heckman or Miragai and Best. So if you would like to use this, there are also different classes than only FR1s and FR2s. So
yeah, I mean, that sounds really helpful. I've been keeping an eye out to try and spot any other catalogs, but I must have missed it.
Oh, it was published 2 years ago. Right now we are preparing the publication of a supplement to this. We had 32,000 of sources. Most of it are compact sources, of course, but there are more than 2,000, and additional more than 2,000 are in this supplement.
Oh, that would be really helpful. Yeah, please, if you wouldn't mind sending that on, I'd very much appreciate it.
Yeah, I actually wanted to do this. I mean, I wanted to write to you because I couldn't find the microphone and earphones. But finally, Grażyna just said that I should say you something about this catalog. So, okay.
Oh no, please do. I really would appreciate it.
Okay, thanks.
Thank you.
Thank you again. I think we can, I don't know if, I think there is no more question. Any more question? No? Okay, so thanks again.
No, thank you.
And thank you to everyone, and see you for our next seminar.
Bon, ça y est.